There's something undeniably thrilling about staring up at the night sky and realizing just how much we still don't understand. The universe is a vast, mysterious playground, filled with wonders that defy logic and phenomena that challenge everything we think we know. And if there's one cosmic puzzle that perfectly embodies this sense of awe and confusion, it's the Crab Nebula. This swirling remnant of a supernova explosion isn't just a beautiful spectacle, it's a hotbed of bizarre, head-scratching activity that has left scientists both fascinated and utterly baffled. From its eerie, pulsing heart to the strange energies crackling through its filaments, the Crab Nebula doesn't just whisper secrets, it shouts them in a language we're still struggling to decode. Imagine a place where time seems to twist, where particles race at speeds that shouldn't be possible, and where bursts of radiation flicker like some kind of cosmic Morse code. That's the Crab Nebula for you, a celestial mystery wrapped in layers of glowing gas and dust. It's not just a relic of a star's dramatic death. It's an active, almost alive phenomenon, constantly surprising us with new riddles. And the deeper we look, the weirder it gets. What's causing those sudden flares of gamma rays? Why does its core behave like nothing else in the known universe? And just how many of its 30 most bizarre quirks can we even begin to explain? That's exactly what we're diving into today, a journey through the most mind-bending, spine-tingling anomalies hidden within this iconic nebula. Some will make you question the laws of physics, others will feel like something straight out of science fiction, but every single one of them is real, happening right now, thousands of light years away. So if you're ready to explore the unexplainable, to venture into a corner of space where the rules don't always apply, then strap in. Because the Crab Nebula isn't just a spectacle, it's a masterclass in cosmic strangeness, and we're about to uncover its deepest, darkest secrets. At the very center of the Crab Nebula lies one of the most mesmerizing objects in the cosmos, a spinning stellar corpse that beats like a heart. This is the Crab Pulsar, a neutron star packing the mass of our Sun into a sphere no larger than a city, rotating 30 times every single second. And with each rotation, it sends out a beam of radiation so precise you could set your watch by it. Well, most of the time, the story of its discovery reads like a cosmic detective tale. Back in 1968, astronomers at the Arecibo Observatory in Puerto Rico were studying radio waves from the nebula when they stumbled upon something extraordinary, a signal pulsing with exact, rapid-fire regularity. At first, some joked it might be aliens trying to communicate, but the truth was even stranger. They'd found the crushed core of the supernova that birthed the nebula, spinning at unimaginable speeds and flinging out beams of energy like a lighthouse cutting through fog. What makes this pulsar truly bizarre isn't just its rhythm, it's the way it sometimes stumbles. Every few years, without warning, the Crab Pulsar experiences what scientists call a glitch. In a fraction of a second, its spin speeds up ever so slightly, throwing off that perfect cosmic metronome. Imagine a dancer mid-performance suddenly twirling faster for no reason. That's essentially what's happening here, except this dancer weighs 1 billion tons and is made of ultra-dense star matter. Theories abound about what causes these glitches. Some suggest cracks forming in the pulsar's crust, like ice on a frozen lake shifting under pressure. Others propose vortices of superfluid neutrons inside the star suddenly unlocking and transferring energy outward. But the real kicker, no model fully explains why these hiccups happen when they do, or why the pulsar always settles back into its rhythm afterward like nothing happened. And then there's the energy. The Crab Pulsar doesn't just spin, it powers the entire nebula around it, energizing those ghostly filaments with charged particles and magnetic fields. It's the engine behind the nebula's eerie glow, making it one of the few places in the universe where we can watch a dead star's heartbeat light up the sky. Yet, even as we study it, this cosmic oddball keeps throwing curveballs, reminding us that when it comes to neutron stars, the universe plays by its own rules. But just when you think the Crab Nebula couldn't get any stranger, it throws another curveball, one so bright and violent it blinds our telescopes. These are the gamma-ray flares, sudden explosions of energy so powerful they outshine the entire nebula for days at a time. And here's the kicker: according to everything we know about physics, they shouldn't even be possible. The first flare caught scientists completely off guard in 2011 when the Fermi Gamma Ray Space Telescope recorded a spike 5 times brighter than the nebula's normal output. Then it happened again and again. Each eruption lasts mere days but pumps out more energy than our sun does in years, all concentrated into bursts of gamma rays, the most lethal form of radiation in the universe. The sheer scale is mind-boggling. Imagine a lightning bolt, but one that stretches light years and carries the energy of a supernova squeezed into a cosmic sneeze. What's truly baffling is where this energy comes from. The Crab Pulsar, normally the nebula's powerhouse, can't explain it. These flares don't sync with its rotation or glitches. Instead, they seem to erupt from the nebula's chaotic magnetic fields, like rubber bands snapping after being twisted too far. Scientists call this process magnetic reconnection, where tangled field lines suddenly realign, converting stored energy into an explosive release. We've seen it happen near Earth and on the Sun, but never at this scale or speed. Some researchers argue there's another player: ultra-relativistic electrons, particles accelerated to near light speed by the pulsar, then whipped into a frenzy by the nebula's turbulence. When these electrons collide with photons, they could theoretically trigger gamma-ray flashes. Yet even this explanation leaves gaps. The energy distribution doesn't quite match, and the flare's rapid rise and fall suggest processes we haven't even modeled yet. What's clear is that these flares rewrite the rules. They challenge our understanding of how particles behave under extreme conditions, forcing us to reconsider decades of astrophysics. Every new detection sends theorists back to their chalkboards, scratching their heads, because in a universe full of mysteries, the Crab Nebula's gamma-ray flares might just be the most defiant puzzle of all, a cosmic middle finger to the laws we thought were set in stone. If the Crab Nebula's pulsar is a cosmic metronome, then its whirling jet is the universe's most hypnotic dance, a searing tornado of particles spinning through space at nearly the speed of light. This high-speed spiral, often called the whirling dervish jet, isn't just a static beam. It's a dynamic, twisting force that contorts itself into knots under the nebula's magnetic chaos. Stretching over half a light year, this jet acts like a particle accelerator on overdrive, flinging matter outward with enough energy to sculpt the surrounding gas into eerie, luminous patterns. What makes this jet truly extraordinary is its sheer violence. Charged electrons and positrons scream along its length, trapped in a corkscrew motion by magnetic fields strong enough to rip atoms apart. These particles don't travel in straight lines, they spiral in helical paths, like water forced down a drain, emitting synchrotron radiation that paints the jet in an otherworldly blue glow. And just when you think it can't get more extreme, Hubble Space Telescope snapshots revealed something startling. The jet isn't stable. It oscillates, wobbling like a spinning top losing balance, its tip whipping back and forth every few months. The culprit behind this instability, the nebula's own magnetic mayhem. Unlike the orderly fields around planets or stars, the Crab Nebula's magnetism is a tangled wreck. Think of it as cosmic spaghetti, with field lines twisted into loops and kinks by the pulsar's furious rotation. As the jet plows through this mess, it encounters resistance, like a river fighting against shifting sandbars. Sometimes the jet even appears to knot up on itself, creating bright bulges where particles collide and release bursts of X-rays. Yet the most baffling part isn't the jet's behavior, it's where these particles come from. The pulsar's surface is too cold to emit them directly, so theorists suspect they're born in the extreme environment just above the neutron star, where magnetic field lines snap and reconnect, launching avalanches of matter into space. It's a process so efficient that it defies earthly comparisons. Imagine a volcano, but instead of spewing lava, it's ejecting a storm of antimatter at 99.9% light speed. What's clear is that this jet isn't just a side feature, it's a fundamental piece of the nebula's engine, pumping energy into its surroundings and shaping its evolution. And like everything else in the Crab Nebula, it refuses to play nice with our expectations, dancing to a rhythm only the cosmos understands. Wrapped around the Crab Nebula's chaotic core is a labyrinth of glowing filaments, delicate, thread-like structures that shimmer with the ghosts of a dead star. These aren't just random wisps of gas, they're a forensic snapshot of the supernova explosion that tore the original star apart, frozen in time and glowing with the energy of their own destruction. Each filament is a cosmic crime scene, rich with elements forged in the star's final moments: oxygen, sulfur, neon, and even traces of iron, all ionized by the pulsar's relentless radiation. What's astonishing isn't just their composition, it's their structure. Unlike the smooth, diffuse clouds in many nebulae, the crab's filaments are shockingly complex, resembling shattered glass or a spider's web caught in a hurricane. Hubble images reveal knots and braids within them, evidence of supersonic shock waves rippling through the debris. Some filaments stretch light years across, while others curl into tight loops, as if the universe itself doodled them into existence. And here's the kicker, they're not just passively glowing. These filaments are alive with motion, expanding outward at over 1,000 kilometers per second, fast enough to cross the United States in less than 5 seconds. But the real mystery lies in what we can't see. Lurking beyond these radiant tendrils, astronomers suspect something far stranger, an invisible halo of dark matter, a gravitational echo of the star that once was. The math doesn't add up without it. The way matter moves within the nebula, the way the filaments twist and accelerate, it all hints at an unseen mass tugging at the fabric of space itself. If it's there, this dark matter shell would be a relic of the original star's outer layers, collapsed into an elusive, shadowy envelope. Dark matter doesn't interact with light, so we'll never see it directly. But its presence could explain why some regions of the nebula defy expectations, with filaments bending in ways that visible matter alone can't account for. Think of it like a ghostly hand shaping smoke. You can't see the fingers, but the way the smoke curls betrays their touch. Some theories even suggest this halo could be home to exotic particles we've yet to discover, relics of the supernova's fury trapped in a gravitational dance. So while the filaments paint a breathtaking portrait of stellar death, the true story of the Crab Nebula might be written in the darkness between them, a story we're only beginning to decipher. Among the Crab Nebula's countless enigmas, few are as visually striking or as downright confusing as the phantom rings that sometimes appear around its pulsar. These eerie, concentric circles aren't solid structures but fleeting illusions, a cosmic magic trick played by shockwaves rippling through the nebula's magnetic chaos. When NASA Chandra X-ray Observatory first spotted them in 2001, scientists were stunned. Nothing in the textbooks predicted this kind of behavior, rings of X-ray light expanding outward like ripples in a pond, except this pond was 6,000 light-years wide and filled with particles moving at nearly the speed of light. What makes these rings so baffling isn't just their appearance, it's their origin. They're not created by the pulsar itself, but by electrons spiraling along magnetic field lines, whipped into frenzy by shockwaves from the neutron star's energetic outbursts. As these high-speed particles collide with photons, they emit X-rays in a process called synchrotron radiation, painting temporary halos onto the nebula's violent canvas. The closer to the pulsar, the tighter the rings. Further out, they stretch into faint, ghostly echoes. But here's the twist, these rings shouldn't be so crisp. According to classical wave theory, such precise, concentric patterns require conditions far more orderly than the Crab Nebula's magnetic hurricane. The leading explanation involves something called magnetic mirrors, regions where the nebula's tangled fields act like funnels, forcing particles into narrow paths that amplify the ring effect. Think of it like sunlight reflecting off uneven water. Normally, you'd expect scattered glimmers, but under just the right conditions, you get a perfect, shimmering circle. The Crab Nebula's magnetic turbulence somehow creates those conditions, bending chaotic energy into brief moments of eerie symmetry. Yet even this explanation leaves gaps. Some rings appear to move faster than the speed of light, an illusion caused by their angle relative to Earth, but one that still defies intuition. Others fade or brighten unpredictably, suggesting pockets of the nebula where physics operates just slightly differently than we expect. It's a reminder that even in death, this star refuses to fit neatly into our models, offering glimpses of a universe far stranger than we imagined. Deep within the Crab Nebula's riot of energy and light, there exist patches of eerie nothingness, regions where the cosmic noise drops to a whisper. These are the radio silence zones, voids where the nebula's usual cacophony of radio waves simply vanishes. It's as if someone hit mute on pockets of space, and the effect is so stark that astronomers first assumed their instruments were malfunctioning. But the silence was real, and the mystery only deepened the closer they looked. The most prominent void sits like a shadow near the nebula's eastern edge, a blotch roughly twice the size of our solar system where radio telescopes detect almost nothing. What makes this especially strange is that radio waves are notoriously hardy. They can travel through dust, gas, and even entire galaxies with little interference. Yet here, in the heart of one of the most energetic environments known, they're being stifled completely. One leading theory points to dense, magnetized plasma acting like a cosmic sponge. In these zones, charged particles could be packed so tightly that they absorb passing radio waves, converting them into other forms of energy before they escape. Imagine shouting into a blizzard, your voice gets swallowed by the snowflakes. Similarly, these waves might be getting scattered and absorbed by turbulent plasma clouds, their signals lost in the chaos. But there's another, wilder possibility: magnetic shadows. The Crab Nebula's fields are so tangled and intense that they could be redirecting radio emissions away from Earth, like a mirror angled just wrong to catch the light. If true, it means these silent patches might not be empty at all. They could be brimming with activity we simply can't detect from our vantage point. The most tantalizing clue comes from X-ray observations. Some silent zones overlap with regions where magnetic field lines appear to knot and twist into bizarre configurations, as if space itself has tied these areas into electromagnetic dead ends. It's a phenomenon without precedent, suggesting that the Crab Nebula isn't just breaking rules, it's inventing new ones. And until we unravel the physics behind these quiet corners, they'll remain some of the universe's most unsettling silences. If you've ever put on a pair of polarized sunglasses and noticed how they cut glare by filtering light waves, you've witnessed a small slice of a phenomenon that's taken cosmic proportions in the Crab Nebula. Here, the entire structure glows with light that's not just bright, it's organized, vibrating in preferred directions like a cosmic fingerprint revealing secrets we're only beginning to decode. This polarization isn't just a curiosity, it's a smoking gun. When astronomers first measured the nebula's light in detail, they found up to 60% of it was polarized, far higher than most celestial objects. That extreme alignment points to one thing: magnetic fields of unimaginable power, stretching across light years and sculpting every particle in their path. Imagine a thunderstorm where every raindrop falls in perfect parallel lines. That's the level of control these fields exert over the nebula's chaos. The real shock came when researchers mapped the polarization patterns. Instead of neat, uniform lines, they found a swirling vortex of magnetic madness. Near the pulsar, the fields twist like DNA helices, wound tight by the neutron star's furious spin. Further out, they splay into chaotic loops, as if space itself were a canvas splattered with magnetic graffiti. These aren't just random shapes, they're evidence of particle acceleration on a scale that dwarfs anything we can recreate on Earth. And that's where the mystery deepens. According to conventional physics, particles gain energy by surfing shock waves or spiraling along field lines. But the Crab Nebula's polarization data suggests something wilder. Regions where electrons are being catapulted to near light speed in ways our models can't fully explain. Some zones show polarization flipping abruptly, like a highway where lanes suddenly switch directions without warning. Others reveal dark regions where the polarization drops to zero, pockets where the rules seem to briefly suspend. One leading theory involves magnetic reconnection gone rogue. Normally, this process releases energy in controlled bursts, like a circuit breaker tripping. But in the Crab Nebula, it might be more like a downed power line thrashing in a hurricane, creating fractal patterns of acceleration that leave even supercomputers stumped. There's also the eerie possibility of quantum effects scaling up tiny particle behaviors, usually invisible, somehow imprinting on the nebula's grand structure. What's certain is that this polarized light isn't just a spectacle, it's a coded message. Every flicker, every twist in those magnetic fields holds clues about how energy moves through the universe's most extreme environments. And until we crack that code, the Crab Nebula will keep its most electrifying secrets locked away. Among the Crab Nebula's most elusive messengers are neutrinos, ghostly particles so indifferent to matter they could pass through light years of lead without a single collision. Yet every now and then, deep underground in detectors like Ice Cube, one of these phantoms leaves a trace, and when scientists trace the paths of a handful back to the Crab Nebula, they found something odd. These neutrinos weren't arriving in a steady trickle. Instead, they came in sporadic bursts, as if the nebula itself were flipping a cosmic switch on and off. What makes these detections so puzzling isn't just their rarity, it's the timing. Neutrinos are born in extreme environments, usually from proton collisions or radioactive decay. In the Crab Nebula, they should emerge like a constant hum from the pulsar's furious particle acceleration. But the data tells a different story. Some years, multiple neutrinos arrive in quick succession. Other times, detectors go silent for a decade. This inconsistency suggests processes we've never observed, perhaps magnetic reconnection, events so violent they briefly flood space with these shadowy particles, or shock waves revving up protons to energies where neutrino production spikes unpredictably. Then there's the antimatter surplus, a discovery that bends the rules even further. The Crab Nebula shouldn't be a factory for positrons, the antimatter twins of electrons, yet observatories have detected them streaming outward at levels far beyond predictions. These particles aren't just rare, they're energetic, carrying enough punch to imply acceleration mechanisms beyond our standard models. Some theorists point to the pulsar's magnetosphere, where twisted magnetic fields might rip apart virtual particles, yanking positrons into reality. Others speculate about quantum vacuum breakdowns, moments where space itself frays under extreme forces, briefly transforming into a particle-generating furnace. The implications are staggering. If the nebula's antimatter output stems from undiscovered physics, it could rewrite our understanding of how matter dominates the universe. Every rogue positron is a clue, a hint that in the crab's chaotic heart, the universe might be playing by rules we've yet to uncover. And until we catch more of these phantom particles in the act, the mystery will linger, a tantalizing gap in the cosmic ledger where antimatter refuses to balance. Beneath the Crab Nebula's grand spectacle of swirling gases and searing radiation lies a subtler, stranger performance, one playing out on a scale so tiny it's easy to overlook. Infrared telescopes have revealed something almost whimsical: countless dust grains, each no larger than a mote of smoke, jerking and darting through space like frenzied fireflies. These particles don't drift lazily, they dance, zipping in abrupt, zigzagging motions that defy the predictable rhythms of cosmic winds. It's as if the nebula has its own microscopic ballet, choreographed by forces we're only beginning to understand. At first glance, this erratic motion seems impossible. In the vacuum of space, dust should move smoothly, carried by the nebula's expansion or gentle magnetic nudges. But the Spitzer Space Telescope's infrared eyes caught something far more chaotic. Some grains accelerate suddenly, as if flicked by an invisible finger. Others spin like tops, their paths looping in tight corkscrews before veering off in new directions. The most puzzling part, these movements don't align with the nebula's larger structure. They're entirely local, as if each patch of dust has its own hidden turbulence. The leading explanation points to electrostatic forces, a cosmic version of static cling gone wild. As the pulsar's radiation bathes the nebula, it strips electrons from atoms, leaving the environment crackling with electric charge. Dust grains bombarded by these particles can become ionized themselves, turning into tiny magnets with unpredictable polarities. When two similarly charged grains approach, they might repel violently, sending one careening away. Other times, oppositely charged particles could snap together like cosmic Velcro before breaking apart again, adding to the chaos. It's a microscopic tug of war where the rules change every millisecond. But there's another layer to the mystery. Some researchers argue that pure electricity can't explain the most extreme jumps. They suspect microturbulent subatomic eddies swirling in the nebula's magnetic fields could be whipping the dust into frenzy. Imagine the particles as leaves caught in a hurricane's gusts, except this storm is invisible, its currents woven from magnetism and particle beams rather than wind. These hidden vortices might arise from shockwaves too faint for our telescopes to detect, or from the pulsar's influence ricocheting through the nebula's tangled interior. What's truly fascinating is what these dancing grains reveal about the nebula's hidden architecture. Their movements trace otherwise invisible forces, mapping out pockets of turbulence and charge we'd never notice otherwise. In a way, they're tiny probes flung into the Crab's storm and reporting back through their erratic paths. And just like the rest of this cosmic enigma, they refuse to behave as expected, reminding us that even in the grand theater of the universe, some of the most captivating performances happen on the smallest stage. In the swirling chaos of the Crab Nebula, even the laws of thermodynamics seem to take a vacation. Normally, heat rises, warm air lifts above cool, boiling water churns to the surface. But here, astronomers have spotted something that flips that basic rule on its head. Temperature inversions, where scorching gas floats stubbornly atop cooler layers like flames licking downward. It's as if someone held a blowtorch under a block of ice and watched the ice stay frozen while the torch itself got colder. These thermal paradoxes cluster in specific regions, particularly near the nebula's twisted inner filaments. Infrared and X-ray telescopes reveal pockets where gas exceeding 2 million degrees Celsius hovers seamlessly above regions 10 times cooler. At first glance, it's like finding a layer of molten lava gently resting on a snowbank, utterly nonsensical unless you account for the Crab's relentless electromagnetic madness. One explanation points to the pulsar's ruthless particle winds. As these high-speed gusts slam into slower-moving gas, they create shock fronts hotter than the sun's core. But instead of dissipating upward, these superheated layers get trapped by the nebula's labyrinth of magnetic fields, which act like invisible ceilings, corralling the heat into floating, searing blankets. Picture a frying pan suspended over water. The pan sizzles while the liquid beneath stays eerily undisturbed. Then there's the turbulence factor. The Crab Nebula isn't just a cloud, it's a blender set to cosmic speed, with supersonic shockwaves ricocheting off each other in unpredictable ways. When these collisions occur at oblique angles, they can compress gas into dense, cool knots while flinging ultra-hot plasma outward in thin veils. It's a celestial version of pouring cold cream into coffee and watching the cream somehow rise to form a steaming layer on top. But the wildest hypothesis involves magnetic reconnection, those same explosive events behind the gamma-ray flares. When field lines snap and realign, they don't just release energy, they can also sculpt it, channeling heat into discrete layers like a cosmic lasagna. Some models suggest these reconnection zones might even briefly create anti-convection cells, where heat flows backward due to magnetic pressure overwhelming normal thermal motion. The implications stretch far beyond this one nebula. If such inversions persist elsewhere, they could rewrite how we model stellar winds, supernova remnants, even the plasmas swirling around black holes. The Crab's thermal defiance isn't just a curiosity, it's a masterclass in how extreme physics bends the rules, proving once again that in the universe's most chaotic corners, the expected is rarely what you get. Among the Crab Nebula's many chemical mysteries, perhaps none is as baffling as the case of the missing heavyweights, the gold, platinum, and uranium that should be here but aren't. When a massive star explodes as a supernova, it's supposed to be a cosmic alchemist's dream, forging elements heavier than iron in its dying moments through rapid neutron capture. Yet when astronomers tally up the Crab's elemental inventory, they find a surprising shortage of these precious metals, as if the universe skipped a step in its own recipe book. This isn't just a trivial discrepancy, it cuts to the heart of how we understand supernova. The process responsible for creating heavy elements, called the R process, short for rapid neutron capture, requires absurdly dense neutron fluxes, the kind thought to occur when a collapsing star's core rebounds in a supernova explosion. For decades, astronomers assumed the Crab Nebula, born from one of history's most famous stellar detonations, would be lousy with R-process debris. Yet spectral analysis reveals far less gold and platinum than predicted, sometimes by factors of 10 or more. It's like cracking open a geode expecting jewels and finding mostly plain rock. One theory suggests the original star wasn't quite massive enough to trigger a robust R process. While it certainly exploded violently, Chinese astronomers recorded the event in 1054 AD. As a guest star bright enough to cast shadows, its core might have fallen short of the extreme densities needed to churn out heavy elements in bulk. Think of it as a bakery oven that never quite reaches the temperature needed to caramelize sugar. The ingredients were there, but the conditions weren't perfect. Another possibility is even stranger, that much of the heavy material didn't escape. Some models propose these elements could have been sucked back into the neutron star's crushing embrace, locked away forever in its ultra-dense interior. Imagine a firework that shoots sparks upward, only for half of them to reverse course mid-air and plunge back into the fuse. If true, it would mean the Crab Pulsar isn't just a dead star's core, it's a vault hoarding the universe's lost treasures. But the plot thickens further. Recent observations hint that the missing metals might be hiding in plain sight, not as atoms but as dust grains too cold for our telescopes to detect. Gold atoms in gas form glow at specific wavelengths, but if they've clumped into microscopic nuggets, they'd be virtually invisible to most instruments. It's the difference between spotting a neon sign and a pile of coins in a pitch-black room. One screams for attention while the other slips under the radar. This gap isn't just a Crab Nebula problem, it's a cosmic one. If other supernova remnants show similar shortages, it could force a rethink of where heavy elements actually originate. Some astrophysicists now speculate that neutron star collisions, not supernova, might be the universe's primary goldsmiths. The 2017 detection of such a collision spewing huge amounts of heavy elements supports this idea. Yet that raises another question. If mergers are the real R process factories, why do some supernovas still produce these materials at all? The Crab Nebula's missing metals are more than a curiosity. They're a cosmic detective story with implications for everything from the chemistry of planets to the origins of life. After all, the gold in your jewelry and the uranium in nuclear reactors had to come from somewhere, and if the Crab's explosion couldn't account for them, it means the universe's periodic table is still missing a few key footnotes. One of the most mind-bending illusions in the Crab Nebula isn't just a trick of the light. It's a full-blown defiance of cosmic speed limits. If you've ever seen time-lapse images of the nebula's jets, you might catch something impossible: bright knots of material screaming outward faster than light itself. Before you panic and rewrite Einstein's theory of relativity, here's the twist. It's all an elaborate cosmic sleight of hand, one that still trips up even seasoned stargazers. This phenomenon, called superluminal motion, plays out like a high-speed cosmic mirage. The jet's material isn't actually breaking the universe's ultimate speed limit. Instead, it's racing toward us at just a hair under light speed while also being blasted sideways by the pulsar's rotation. The combination creates an optical illusion where the jet's approaching motion compresses the light's travel time, making it appear to move faster than reality allows. Imagine a motorcycle speeding toward you while doing donuts. If it's close enough, the sideways spin might make the headlight seem to streak across your vision unnaturally fast, even though the bike itself isn't moving sideways at that speed. The math behind this is both elegant and brain-melting. As material in the jet barrels toward Earth at nearly 99% light speed, each new burst of light has less distance to travel to reach us than the one before it. Our brains and even some telescopes interpret this as the object covering vast distances in impossibly short time, like watching a strobe light flicker on a train rushing toward you. The effect peaks when the jet's angle aligns just right with our line of sight, amplifying the illusion to absurd extremes. Some features have appeared to move 10 times the speed of light, a trick that's left more than a few amateur astronomers scratching their heads. But here's where it gets even weirder. This isn't just a static illusion. The jet's wobble means the angle shifts over time, causing the apparent speed of these features to fluctuate wildly. One year, a knot might seem to crawl along at half-light speed. The next, it could accelerate to 20 times that. It's a reminder that in astrophysics, perspective isn't just everything. It's the difference between impossible and merely improbable. What makes this illusion so persistently confusing is how it clashes with everyday intuition. We're used to things moving in straight lines at sensible speeds, not contorting spacetime's rules through relativistic gymnastics. Even professional astronomers initially doubted their instruments when they first observed it decades ago. Today, it stands as one of the Crab Nebula's greatest teaching tools, proof that the universe doesn't just play by its own rules, but sometimes rewrites them right before our eyes. The Crab Nebula's ever-changing landscape hides fleeting specters, mysterious clumps of gas that materialize out of nowhere, glow fiercely for a few years, then vanish without a trace. Astronomers call them ghost knots, and they're some of the most enigmatic features in this already bizarre cosmic expanse. Unlike the nebula's more permanent structures, these knots appear suddenly, often in regions that were empty just months earlier, burning bright before dissolving back into the chaos. It's as if the nebula itself is whispering secrets, only to snatch them away before we can fully listen. One of the most famous ghost knots flared to life in 2005, appearing near the nebula's northwestern edge like a cosmic firework. Hubble Space Telescope images captured it as a brilliant, compact blob, shining with ionized oxygen and sulfur. Yet within 3 years, it had faded to near invisibility, leaving behind no obvious trace. What makes these apparitions so puzzling isn't just their transience, it's their defiance of conventional physics. Gas clouds in space don't just vanish, they dissipate slowly like smoke in a gentle breeze. But these knots wink out as if someone flipped a switch, suggesting forces at work beyond simple expansion. The leading theory points to the nebula's extreme magnetic fields. Imagine a rubber band stretched to its limit. When it finally snaps, the recoil releases energy in a sudden, localized burst. Similarly, twisted magnetic field lines in the Crab Nebula might pinch pockets of gas, compressing them until they glow intensely. But once the tension eases, the knot unravels, its material scattering too thinly to detect. This process, called magnetic reconnection, is the same phenomenon behind solar flares, but in the Crab, it operates on a scale and intensity unmatched anywhere else in the known universe. Yet not all ghost knots fit this explanation. Some seem to emerge from turbulent collisions between the pulsar's high-speed winds and slower-moving gas. These smash-ups can create temporary density spikes, cosmic traffic jams where particles pile up, emit a flash of light, then disperse as the shockwave passes. Think of it like waves crashing on a shore. For a moment, water foams into a towering crest, only to collapse back into the sea. In the Crab Nebula, these chaotic interactions might leave behind glowing scars that fade as quickly as they form. Then there's the strangest possibility of all, quantum effects scaling up. In labs on Earth, physicists observe particles popping in and out of existence due to quantum fluctuations. While these phenomena normally play out on subatomic scales, the Crab's extreme environment could magnify them, creating momentary concentrations of energy dense enough to briefly light up like miniature stars. It's a fringe idea, but if true, it would mean some ghost knots aren't even made of ordinary matter. They're quantum hiccups, visible reminders that the universe is far weirder than it seems. Whatever their origin, these ephemeral knots serve as a reminder that the Crab Nebula is anything but static. It's a dynamic, evolving beast where even the smallest features can rewrite the rules. And with every vanished knot, the nebula seems to tease us, hinting at hidden processes we've yet to unravel, and leaving us to wonder what other ghosts might flicker to life in its depths tomorrow. Hidden within the Crab Nebula's tangled depths is a natural particle accelerator so powerful it makes Earth's most advanced colliders look like toys, a relentless factory churning out cosmic rays, those high-energy subatomic bullets that constantly rain down on our planet. These aren't just ordinary particles, they're protons and atomic nuclei whipped up to velocities approaching light speed, carrying energies millions of times greater than anything we can produce in laboratories. And the Crab's assembly line operates on an unimaginable scale, firing these cosmic projectiles across interstellar space like a cosmic Gatling gun. What makes this process so extraordinary is how it defies conventional acceleration methods. On Earth, we rely on massive machines with carefully tuned electromagnetic fields to push particles faster. But the Crab Nebula achieves the same result through pure chaos. Its pulsar's magnetic field, spinning at dizzying speeds, creates a natural cyclotron effect. Charged particles get trapped in these whirling fields, gaining energy with each loop until they're finally flung outward like sparks from a grinding wheel. Some end up embedded in the nebula's filaments, while others escape entirely, eventually crossing paths with Earth as cosmic rays. The real jaw-dropper comes when we measure their energy. The highest energy cosmic rays detected from the Crab's direction pack over 1 quadrillion electron volts, enough punch to briefly outshine the entire output of our Sun, all concentrated into a single proton. To put that in perspective, that's like a single grain of sand hitting you with the force of a major league fastball. These extreme energies suggest acceleration mechanisms beyond our current models, possibly involving cascading shockwaves or magnetic reconnection events that stack energy upon energy until particles reach these staggering velocities. Then there's the spectral oddity that's had nuclear physicists scratching their heads for decades. An unexpected spike in ion emissions that shouldn't exist. When astronomers analyzed the Crab's light signature, they found ion spectral lines glowing far brighter than any standard supernova model predicts. Ion typically forms deep within massive stars just before collapse, but the amounts detected here imply nuclear processes operating at efficiencies we've never observed. One controversial explanation involves the pulsar's magnetosphere acting as a nuclear crucible. under its extreme magnetic pressures, ordinary matter could be transmuted into heavier elements through processes resembling cold fusion, except occurring at temperatures hotter than the Sun's core. Another theory suggests chunks of the original star's iron-rich core were vaporized in the explosion, then recondensed into ultra-dense clusters that now glow intensely under the pulsar's relentless radiation. The implications ripple far beyond this one nebula. If the Crab's cosmic ray production is more efficient than we thought, it could rewrite our understanding of how these particles permeate the galaxy. And if that iron spike hints at unknown nuclear pathways, it might mean our charts of stellar element formation are missing entire chapters. In both cases, this swirling stellar graveyard continues to teach us that the universe's rulebook has pages we're only beginning to turn. The Crab Nebula's magnetic field isn't just strong, it's a cosmic Jackson Pollock painting, a frenzy of lines and loops that twist, kink, and tangle in ways that defy the very theories meant to explain them. Imagine trying to map the path of a lightning bolt during a hurricane, and you'll get a hint of the chaos astronomers face when studying this nebula's magnetism. Unlike the orderly fields around planets or stars, where lines run smooth like the grooves on a vinyl record, the Crab's magnetic architecture is more like a smashed record, shattered, warped, and crackling with unpredictable energy. Polarized light imaging has been the key to unraveling this mess, revealing patterns that look less like a magnetic field and more like a cosmic riot. When light passes through magnetized gas, its waves align along the field's direction, like iron filings tracing the shape of a bar magnet. In the Crab, this polarization paints a picture of relentless turmoil. Near the pulsar, the field coils into tight spirals, twisted by the neutron star's furious spin like taffy being pulled. Further out, it fractures into jagged loops and braids, some snapping like overstretched rubber bands before reforming seconds later. The most perplexing regions show polarization flipping 180 degrees over distances shorter than our solar system magnetic whiplash on a scale that leaves theorists reeling. This level of disorder throws a wrench into classic dynamo theories, which predict that rotating, conductive fluids like those in stars or planets should generate fields with some semblance of symmetry. But the Crab's pulsar isn't playing by those rules. Its dynamo seems more like a drunk sculptor, molding magnetic clay into shapes that change faster than we can track. One leading hypothesis suggests the original supernova explosion didn't just collapse the star's core, it shattered its magnetic legacy, leaving behind a fractal nightmare of competing fields. Another idea points to the pulsar's wind, a supersonic river of particles that slams into slower moving gas, crumpling the field lines like paper in a fist. Then there's the sheer violence of the field's behavior. Some zones exhibit magnetic strengths exceeding 1 milligauss weak by Earth standards, but extraordinary for a structure light years across. These patches don't just bend light, they act like cosmic particle slingshots, hurling electrons to velocities that should tear them apart, and yet they don't. It's as if the field's chaos somehow stabilizes the very processes that ought to destabilize it. A paradox that's forced physicists to reconsider how magnetism operates in extreme environments. The implications stretch far beyond this one nebula. If magnetic fields can sustain this level of complexity without dissolving into noise, it could reshape how we model everything from jet-forming black holes to the birth cries of galaxies. The Crab's twisted magnetism isn't just a curiosity, it's a challenge, a dare to the textbooks. And until we crack its code, we're left staring at a cosmic puzzle where the pieces keep changing shape. Deep within the Crab Nebula's glittering chaos, light doesn't just travel, it lingers, bouncing off cosmic walls like whispers in a cavern. These are light echoes, ghostly reflections from the original supernova explosion that have been ricocheting through space for nearly 1,000 years. While the main flash faded centuries ago, subtle afterglows still reach us, delayed by their indirect paths through the nebula's maze of dust and gas. It's like hearing thunder roll in long after the lightning strike, except here, the thunder is made of photons that have taken scenic detours across light years before finally washing over Earth. The discovery of these echoes was a masterstroke of cosmic archaeology. Back in 2005, astronomers comparing Hubble images noticed faint, expanding rings of light around the nebula, not part of its structure, but something far more ephemeral. These ripples were the scattered remnants of the supernova's initial blast, photons that had bounced off interstellar dust clouds hundreds of light years behind the Crab. Because these detours added extra distance, the light arrived centuries late, offering a time-lapse replay of the explosion's aftermath. The implications were staggering. For the first time, we could effectively watch the supernova's light curve evolve in real time just by tracking these delayed echoes. But the real breakthrough came when scientists used these echoes to pin down the exact date of the explosion. Historical records pointed to 1054 AD, when Chinese and Arab astronomers documented a guest star bright enough to cast shadows at night. The light echoes confirmed it by measuring how far the echoes had traveled and comparing their spectra to modern supernova models. Researchers could backtrack the light's journey to within a few years of those ancient observations. It was as if the universe itself had preserved a receipt for its own cataclysmic event, time-stamped and glowing faintly in the void. These echoes don't just mark time, they map space. The way they fan outward reveals the nebula's three-dimensional structure, exposing cavities and dust lanes invisible to direct observation. Some echoes curve around the backside of the nebula, proving the explosion wasn't perfectly spherical. Others fragment into jagged patterns, hinting at shock fronts where the blast wave plowed into pre-existing stellar winds. It's a forensic tool unlike any other, turning photons into detectives that reconstruct the crime scene of a star's death. Perhaps most astonishing is what the echoes say about the nebula's expansion. By comparing their modern positions to earlier records, astronomers have clocked the outer filaments racing outward at nearly 1,500 kilometers per second faster than previous estimates. This acceleration suggests the nebula's guts are even more turbulent than we thought, with the pulsar's winds shoving against the debris like a cosmic snowplow. Yet some inner regions lag behind, trapped in magnetic eddies that break their motion. The result is a celestial tug-of-war written in light that took 10 centuries to reach us. In a way, these echoes are more than just relics, they're time machines. Each photon carries a snapshot of the supernova's fury at a specific moment, allowing us to piece together its evolution frame by frame. And as new echoes continue to emerge from the depths of the nebula's dust clouds, they promise fresh revelations about one of history's most violent stellar farewells, a death thrum still resonating across the ages. Beyond the Crab Nebula's familiar tendrils of gas and light lies a ghostly shroud, a vast, faint halo glowing softly in infrared wavelengths. This ethereal envelope stretches far beyond the nebula's visible boundaries, a diffuse whisper of cold dust suspended in space. Unlike the violent brilliance of the inner nebula, this halo is subtle, requiring instruments like NASA's Spitzer Space Telescope to tease out its delicate details. Yet its presence raises profound questions. Is this the lingering breath of the star that died here, or something far stranger? The halo's composition offers the first clue. Its infrared signature points to temperatures just a few dozen degrees above absolute zero, so cold that ordinary telescopes would miss it entirely. These frigid dust grains are likely flecks of carbon and silicates, the cosmic equivalent of soot and sand drifting through the void. But their distribution is anything but random. Instead of fading evenly into space, the dust forms a lopsided shell, thicker on one side as if sculpted by an ancient stellar wind. That asymmetry suggests this material wasn't just ejected in the supernova explosion. Some of it might have been shed by the doomed star centuries before its final cataclysm. This idea ties into a controversial theory about massive stars in their death throes. In the millennia before a supernova, aging stars often become unstable, shedding layers of material in erratic gusts. For the Crab's progenitor, these pre-explosion winds could have carved a cavity in the surrounding interstellar medium, like a snowplow clearing a path before a crash. When the star finally detonated, the blast wave would have plowed into this pre-existing dust, heating some to incandescence while leaving the outermost regions relatively undisturbed. The result, a fossilized bubble of cold debris preserved like a cosmic time capsule. Yet alternative explanations abound. Some researchers argue the halo could be interstellar dust material entirely unrelated to the supernova, merely illuminated by the nebula's glare. Others propose a hybrid scenario where the star's winds mixed with ambient dust long before the explosion, creating a patchy cocoon later reshaped by the blast. The most tantalizing possibility involves exotic chemistry. These dust grains might not be simple silicates but complex macromolecules, even prebiotic compounds forged in the supernova's crucible. If true, the Crab's halo could be a nursery for the building blocks of life, scattered across light years by stellar death. The debate hinges on motion. If the halo's dust is truly ancient, it should drift outward at predictable speeds. But recent observations reveal something odd. Some regions appear stationary, as if pinned by invisible forces. This could point to magnetic fields threading the dust, or perhaps gentle pressure from the pulsar's wind slowing its expansion. Either way, the halo refuses to behave as models predict, adding yet another layer of mystery to the Crab's ever-deepening enigma. What's certain is that this infrared spectre holds secrets about stellar life cycles we've barely begun to uncover. It's a reminder that supernova aren't just explosive ends, they're chapters in a longer story, one written in dust and light across millennia. And as telescopes grow more sensitive, the Crab's faint halo may yet reveal truths about the star that birthed it, whispering across the centuries in a language only now becoming clear. Tucked away in the Crab Nebula's turbulent expanse are two chemical oddities that shouldn't coexist, yet they do, defying expectations with every observation. The first is a series of sodium-rich gas clumps rocketing through space at breakneck speeds, leaving vapor trails of orange light in their wake. These aren't your typical stellar debris, they're cosmic speedsters, some clocking velocities over 2,000 kilometers per second. Fast enough to cross the continental United States in under 2 seconds. What's baffling isn't just their speed, it's their composition. Sodium isn't usually a standout player in supernova remnants, yet here it's glowing brighter than textbook models predict, as if the explosion singled out this element for a violent encore. The leading theory suggests these clumps might be fragments of the progenitor star's outer layers, violently shredded during the explosion and injected with extra energy by the pulsar's relentless winds. Picture a log tossed into a river. Normally, it'd drift lazily, but if you strapped a rocket to it, it'd outpace the current. That's essentially what's happening here, except the rocket is the pulsar's magnetic field, accelerating select pockets of gas to ridiculous speeds. But why sodium? One possibility points to the star's pre-explosion chemistry. In its final millennia, the dying giant might have dredged up sodium-rich material from deep within its core, seeding its outer atmosphere with this unexpected element before the supernova scattered it like confetti. Now shift your gaze slightly, and you'll spot the second anomaly, helium-rich zones glowing like cosmic bruises amid the nebula's tapestry. These regions aren't just helium-enhanced, they're helium-dominated, with concentrations up to 10 times higher than the surrounding gas. This imbalance is a forensic clue, hinting that the supernova didn't eject its material evenly. Instead, it might have erupted in spasms, with distinct layers of the star's interior expelled at different moments or angles. Imagine shaking a soda can and poking holes in it. Some spray would be fizzier than others. Similarly, these helium pockets could represent bursts where the star's helium shell broke through heavier overlying layers, escaping almost untouched. What's truly bizarre is how these helium zones avoid mingling with their surroundings. You'd expect a supernova's violence to churn everything into homogeneity, yet these regions remain stubbornly distinct like oil droplets in water. Some astrophysicists suspect magnetic fields might be corralling the helium, preventing diffusion. Others propose these are actual chunks of the star's intermediate layers, flung outward so fast they didn't have time to mix. Either way, their existence challenges assumptions about how stars distribute their guts during these catastrophic explosions. Together, these phenomena paint a picture of a supernova that wasn't just powerful, it was selective, even capricious. The sodium jets scream through space like cosmic afterthoughts, while the helium patches linger like stubborn stains, refusing to blend in. It's a reminder that stellar deaths aren't tidy affairs. They're messy, chaotic, and full of surprises. And in the Crab Nebula's case, those surprises are still writing themselves across the sky, one anomalous element at a time. Just when scientists thought they'd catalogued all the Crab Nebula's gamma-ray surprises, it started throwing tantrums, brief but dramatic dips in its high-energy output that astronomers have nicknamed hiccups. These aren't your typical fluctuations. Over mere hours, the nebula's gamma-ray emissions can plummet by as much as 20% before snapping back to normal like a cosmic rebound. It's as if something inside this stellar wreckage periodically chokes on its own energy, leaving telescopes blinking in confusion. The first hiccup caught researchers off guard in 2017 when NASA's Fermi Gamma-Ray Space Telescope recorded an abrupt drop in the Crab's normally steady gamma-ray signal. At first, they suspected instrument error. After all, this nebula has been astronomy's standard candle for high-energy emissions for decades, its output as reliable as a metronome. But when the pattern repeated short, sharp declines followed by rapid recoveries, they realized they were witnessing something fundamentally strange, even for the Crab. What makes these hiccups so puzzling is their sheer speed. Magnetospheric processes usually unfold over days or weeks, but these dips happen in under 6 hours. That timescale points to something small and incredibly dynamic, perhaps a sudden kink in the pulsar's magnetic field near its surface, where charged particles get momentarily trapped instead of being ejected. Think of it like a kinked garden hose. Water pressure builds, flow stutters, then releases with a jerk when the obstruction clears. But there's a wilder possibility dancing at the edges of quantum physics. Some theorists suggest these hiccups could stem from vacuum breakdowns, moments when the pulsar's intense magnetic field rips apart the fabric of space itself. According to quantum electrodynamics, a vacuum isn't truly empty. It's a seething foam of virtual particle-antiparticle pairs flickering in and out of existence. Under normal circumstances, these pairs annihilate too quickly to notice, but in magnetic fields exceeding 1 trillion Gauss, like those near the Crab pulsar, something extraordinary happens. The field can pry these virtual particles apart before they vanish, converting them into real electrons and positrons in a process called vacuum polarization. If this phenomenon spikes unpredictably, it might briefly sap energy from the nebula's gamma-ray production, creating the observed dips. Imagine a factory where conveyor belts occasionally jam because invisible hands keep stealing widgets off the line. That's essentially what might be happening on a quantum scale within the pulsar's magnetosphere. Yet even these exotic explanations have gaps. The hiccups don't correlate with the pulsar's glitches or its rotation period, leaving no clear trigger. Some researchers argue they might be tied to magnetic reconnection, events too small to detect directly, tiny, short circuits in the field lines that divert particle flows momentarily. Others propose resonant oscillations in the pulsar wind, where waves of pressure briefly throttle the outflow like a singer shattering glass with the right note. The implications stretch far beyond this one nebula. If vacuum effects or nanoscale reconnection can alter high-energy emissions this dramatically, it challenges our models of particle acceleration across the universe. These hiccups might be microscopic disturbances, but they're punching holes in macroscopic theories, proving once again that the Crab Nebula saves its weirdest tricks for when we least expect them. The Crab Nebula doesn't just sit still, it breathes, its glowing tendrils writhing and reshaping over years like a living thing. Time-lapse images spanning decades reveal a structure in constant flux, filaments surging outward in some areas while collapsing inward in others, as if the nebula itself is caught in an endless cosmic tug-of-war. This isn't some slow, stately expansion. It's a dynamic dance of forces where the pulsar's furious winds battle against the lingering resistance of ancient stardust. Hubble's snapshots tell the story best. Compare images from 1999 to today, and you'll spot filaments near the nebula's core stretching thin, like taffy pulled too far, while outer regions billow outward in uneven bursts. Some gas knots race ahead at 1,500 kilometers per second, while others lag behind, trapped in magnetic eddies or slowed by collisions with older debris. The most dramatic shifts occur along the jet's path, where the pulsar's focused particle beam carves through the nebula like a blowtorch, reheating gas and forcing it into new configurations. But even these changes aren't uniform. Some sections of the jet wobble unpredictably, their tips flicking sideways as if shoved by invisible hands, while other segments hold their line with eerie precision. The driving force behind this restlessness, a relentless showdown between two titanic pressures. On one side, the pulsar's wind, a supersonic river of charged particles barrels outward, injecting fresh energy into the nebula's heart. On the other, the weight of interstellar material and the nebula's own tangled magnetic fields push back, creating shock fronts that ripple through the structure like seismic waves. Where these forces collide, the gas can't settle. It compresses, heats up, and gets flung aside, only to encounter another shock wave and repeat the cycle. It's like watching smoke from a fire twist in the wind, except here, the wind is made of antimatter and the smoke is stellar guts forged in a 1,000-year-old explosion. Yet there's another player in this drama, the nebula's own past. The original supernova didn't eject its material in a clean sphere. It blasted it outward in clumps and streams, leaving behind a minefield of density variations. When the pulsar's modern-day wind hits these fossil imbalances, it doesn't flow smoothly. It stutters, diverting around some obstacles while bulldozing others. The result, a nebula that doesn't expand so much as convulse, its structure morphing in ways that defy simple models. The most telling detail lies in the filaments' braided patterns. Over time, some develop helical twists, as if the gas is being spun by invisible drill bits. This isn't just artistic chaos, it's the signature of magnetic fields wrapping around the nebula's axis, their lines tightening like coiled springs. In a few spots, these spirals even seem to knot, creating bright, tangled junctions where particles pile up and glow fiercely before snapping apart. It's a reminder that the crab isn't just expanding into empty space. It's wrestling with its own electromagnetic skeleton, a framework that guides and sometimes strangles its growth. What's truly humbling is the scale of this metamorphosis. The nebula isn't just tweaking its appearance, it's reinventing itself, shedding old structures and birthing new ones on human timescales. Most cosmic processes unfold too slowly for us to witness, but the crab delivers front-row seats to its own reinvention. And every twist, every surge whispers the same lesson. Even in death, stars refuse to stay still. Their remnants live, breathe, and evolve, daring us to keep up. The Crab Nebula doesn't just scream in gamma rays and writhe in magnetic chaos, it sings. Deep within its turbulent heart, radio telescopes have picked up something haunting. Ultra-low-frequency plasma waves rippling through the gas like the deepest notes of a cosmic cello. These aren't ordinary electromagnetic pulses. They're pressure waves, literal sound traveling through the nebula's searing plasma, so low in pitch that if they were audible, they'd vibrate your bones for years between each tone. What makes these waves so mesmerizing isn't just their existence, it's their sheer scale. Imagine a sound wave so vast it could stretch from Earth to the Moon and back a dozen times before completing a single oscillation. That's the wavelength we're dealing with here, a vibration slow enough to make glacial shifts seem frantic. Yet despite their sluggish pace, these waves carry staggering energy, twisting the nebula's magnetic fields like taffy as they pass. They're not just background noise, they're sculptors subtly shaping the environment around them. The origin of these plasma songs is as mysterious as their sound would be eerie. One leading theory points to the pulsar's relentless wind, a supersonic stream of particles that slams into slower-moving gas, creating shock waves that reverberate through the nebula like a bell struck by a hammer. But there's a hitch: these waves don't match the pulsar's rotation or its known glitches. Instead, they seem to emerge from the nebula's deeper chaos, perhaps from magnetic reconnection events or turbulence in the plasma itself. It's as if the nebula has its own hidden orchestra, playing a score written in forces we can't yet decipher. Even stranger is how these waves interact with their surroundings. Unlike sound on Earth, which dissipates quickly, these plasma oscillations can persist for weeks, even months, their energy slowly leaking into the nebula's filaments. Some regions amplify them, acting like resonant chambers where the waves grow louder as they bounce between magnetic mirrors. Others dampen them abruptly, as if the nebula has acoustic black holes that swallow specific frequencies whole. This patchwork response suggests the Crab isn't just a passive stage for these waves. It's an active participant, tuning and distorting them in ways that challenge our understanding of plasma physics. Then there's the eeriest detail of all: harmonics. Just as a musical note has overtones, these plasma waves sometimes ripple outward in nested frequencies, creating interference patterns that resemble cosmic chords. Some researchers speculate these harmonics might trace hidden structures within the nebula, invisible magnetic skeletons or density variations too faint to see directly. It's like sonar for the universe, using sound to map the intangible. Yet for all we've learned, the Crab's song remains a riddle wrapped in a vibration. Why do some waves vanish without a trace while others linger? How can plasma so turbulent produce such coherent tones? And what, if anything, do these oscillations mean for the nebula's evolution? Each question pulls us deeper into the physics of extreme environments, reminding us that even in the deafening void of space, silence is an illusion. The universe hums with hidden music, and the Crab Nebula, it's singing one of the most haunting melodies of all. Scattered across the Crab Nebula's vibrant tapestry are shadowy voids that absorb ultraviolet light like cosmic sponges, regions where the nebula's usual brilliance dims inexplicably. These ultraviolet dark spots, invisible to optical telescopes, emerge only when astronomers compare Hubble's UV snapshots with images taken in other wavelengths. Unlike ordinary dust clouds that simply scatter or block light, these patches seem to consume high-energy photons selectively, leaving behind spectral fingerprints that hint at something far stranger than mere gas and dust. The leading suspect, molecular hydrogen, cold, dense clumps of paired hydrogen atoms that form naturally in the quiet corners of space. In most nebulae, these molecules get shredded by radiation, but the Crab's extreme environment might be sheltering them in unexpected ways. Magnetic fields could be corralling these fragile clouds into protective knots, shielding them long enough to cast these ultraviolet shadows. Imagine a snowball surviving inside a blast furnace by hiding behind an invisible deflector. That's the level of defiance we're talking about here. Yet the plot thickens when you examine the absorption patterns. Some dark spots exhibit spectral lines that don't match any known molecules, suggesting exotic chemistry at play. One tantalizing possibility involves polycyclic aromatic hydrocarbons, complex carbon-based molecules that thrive in harsh cosmic environments. On Earth, these PAHs are found in everything from engine soot to barbecue grills, but in the Crab Nebula, they might form vast, intricate structures that act like UV-absorbing carpets. Alternatively, the spots could harbor entirely new forms of matter, like quark nuggets or condensates predicted by quantum field theory, particles so dense they interact with light in ways we've never observed. The weirdest part, these dark spots aren't static. Over years of observations, some have shifted position or faded entirely, as if the nebula is erasing its own shadows. This volatility rules out simple explanations like static dust lanes. Instead, it points to dynamic processes, perhaps magnetic vortices that temporarily concentrate absorbing material before dissipating, or shock waves that periodically expose hidden chemistry to the pulsar's glare. What's at stake here isn't just a few cosmic dimples. If these spots contain complex molecules, they could be proof that supernova remnants are cosmic petri dishes, churning out the raw ingredients for life even amid chaos. And if there's something else entirely, well, that would mean the Crab Nebula is still writing chapters in the book of physics we didn't even know existed. Either way, these ultraviolet voids are more than empty space. They're windows into the nebula's best-kept secrets. Drenching the Crab Nebula in an invisible downpour, torrents of high-energy electrons cascade through its chaotic expanse like a cosmic thunderstorm. These aren't your everyday electrons. They're accelerated to nearly light speed, carrying energies so intense they outshine the output of entire stars. Telescopes tuned to X-ray and gamma-ray wavelengths reveal them as streaks of brilliance, tracing the nebula's tangled magnetic fields like raindrops on a window pane. But this isn't just a gentle drizzle. It's a full-blown deluge with particles slamming into gas filaments so violently they generate shockwaves visible across the electromagnetic spectrum. The source of this electron rain is as dramatic as its effects. The Crab pulsar acts like a colossal particle accelerator, its spinning magnetic field whipping electrons into a frenzy before flinging them outward in a supersonic wind. As these charged particles collide with slower-moving material, they don't just slow down, they release energy in cascading bursts, lighting up the nebula's structure like a neon sign. Some electrons spiral along magnetic field lines, their paths curving so tightly they emit synchrotron radiation, painting the nebula in its characteristic blue glow. Others plow straight into gas clouds, transferring their energy with enough force to heat the surrounding material to millions of degrees. It's a perpetual energy exchange, with the pulsar as the relentless storm cloud and the nebula as the ground beneath, absorbing every electrifying drop. Yet for all their fury, these electrons are just half the story. The real shocker comes when scientists tally up the antimatter. Amidst the electron downpour, there's an unexpected surplus of positrons, antimatter counterparts to electrons, streaming from the nebula at levels that defy conventional physics. Positrons shouldn't be this abundant in nature. They're notoriously fleeting, annihilating instantly upon contact with ordinary matter. But the Crab Nebula seems to be manufacturing them on an industrial scale, producing far more than any known process should allow. The leading explanation dives into the pulsar's magnetosphere, where conditions resemble something from a quantum physicist's wildest dreams. Here, magnetic fields grow so intense they warp the fabric of space itself, tearing virtual particle-antiparticle pairs from the vacuum. Normally, these pairs would vanish as quickly as they appeared, but the pulsar's energy yanks them into reality, creating a fountain of electrons and positrons. This phenomenon, known as pair production, might explain the positron excess except for one glaring hiccup. The numbers still don't add up. The nebula's positron output overshoots theoretical predictions by orders of magnitude, suggesting there's another, even more exotic mechanism at work. Some theorists point to magnetic reconnection events, explosive rearrangements of the nebula's field lines as potential positron factories. When these fields snap and realign, they don't just release energy, they can also accelerate particles to velocities where spontaneous pair production kicks into overdrive. Others speculate about neutron star quirks like surface hotspots, where temperatures spike enough to rip particles directly from the pulsar's crust. And then there's the most radical idea of all, that the Crab Nebula's positrons hint at undiscovered physics, perhaps even particles or interactions outside the standard model. What's undeniable is how these phenomena intertwine. The electron rain and positron excess aren't separate curiosities. They're two sides of the same electrifying coin, a testament to the nebula's ability to bend the rules of particle physics. Together, they paint a picture of an environment where matter and antimatter dance on the edge of impossibility, challenging our understanding of how the universe works at its most fundamental level. And with every new observation, the Crab Nebula tightens its grip on these mysteries, daring us to dig deeper into the storm. Among all the Crab Nebula's cosmic contradictions, none is as quietly unsettling as what isn't happening: the pulsar's eerie gravitational silence. Neutron stars, especially rapid rotators like the Crab Pulsar, should theoretically ripple spacetime itself with gravitational waves, the same way a spinning sprinkler sends vibrations through a garden hose. Yet despite decades of searching, detectors like LIGO and Virgo have heard nothing. It's as if this hyperactive stellar corpse is spinning on a frictionless axis, leaving spacetime utterly unfazed. This absence isn't just puzzling, it's revolutionary. Most neutron stars produce gravitational waves through tiny deformities called mountains, bumps on their surface no taller than a few millimeters. As these imperfections rotate, they warp spacetime, emitting faint but detectable ripples. The Crab Pulsar, with its furious 30 Hz spin and extreme magnetic fields, should be a gravitational wave powerhouse. Instead, it's a cosmic mime, performing all the right motions without making a sound. One explanation cuts to the heart of neutron star physics: perfect symmetry. If the pulsar's crust is flawlessly smooth, a sphere polished to atomic-level precision by unimaginable gravitational forces, there'd be no mountains to generate waves. But achieving such perfection defies probability. Even a single misplaced atom would create a deformity, yet the crab's silence suggests something far stranger. A crust so fluid it heals imperfections instantly, like a lake smoothing out a pebble splash before the ripples can spread. There's a wilder possibility. Some theorists argue the pulsar's interior might be a superfluid so exotic it freezes spacetime distortions before they can propagate. Picture spinning a marble in molasses. The thick fluid resists creating waves, absorbing the energy internally. In the crab's core, quantum effects scaled up to stellar proportions could be acting like that molasses, damping gravitational waves at their source. If true, it would mean neutron stars aren't just dense, they're cosmic shock absorbers, bending the rules of general relativity in ways Einstein never anticipated. The implications ripple far beyond this one nebula. If the Crab Pulsar's silence stems from ultra-rigid spacetime, it challenges our understanding of how matter behaves under extreme conditions. Other neutron stars emit gravitational waves just fine, meaning the crab might represent a rare subclass object so perfectly balanced they slip through the cracks of spacetime itself. Alternatively, its magnetic fields could be warping local geometry, creating a quiet zone where gravitational waves cancel out like noise-canceling headphones for the universe. Whatever the reason, this gravitational hush is more than a curiosity, it's a cosmic provocation. The Crab Nebula has spent 1,000 years dazzling us with its light show. Now it's teaching us that some of the universe's most profound lessons come not from what's seen or heard, but from the silence in between. Among the Crab Nebula's countless enigmas, none is as tantalizing or as controversial as the whisper of primordial matter hiding in plain sight. Isotopic anomalies scattered throughout its filaments suggest something extraordinary. Trapped within this stellar wreckage might be atoms older than the supernova itself, cosmic relics dating back to the star's infancy. If true, it would mean the Crab Nebula isn't just a graveyard, it's a living fossil preserving fragments of a universe long gone. The evidence lies in the subtle fingerprints of certain elements. When astronomers analyzed the nebula's spectral lines, they stumbled upon ratios of isotopes, variants of elements with differing numbers of neutrons that defy expectations. Take neon, for example. The Crab's outer filaments show a neon 22 to neon 20 ratio, nearly double what standard supernova models predict. This imbalance is no fluke, it's a smoking gun. Neon 22 is typically forged in the slow-burning furnaces of massive stars long before they explode, meaning these excess pockets could be untouched remnants of the progenitor star's earliest layers, somehow surviving the detonation unscathed. But the anomalies don't stop there. Sulfur isotopes in some regions skew unexpectedly heavy, while argon measurements reveal patches where lighter variants dominate. These inconsistencies point to material that never reached the supernova's hellish core, avoiding the nuclear alchemy that normally homogenizes a star's contents during collapse. Picture a tree caught in a wildfire while most of it burns to ash. A few buried roots might remain intact beneath the soil. Similarly, the Crab's outer layers may have shielded slivers of primordial gas, preserving them like time capsules in the ejector. The implications are staggering. If these ancient atoms exist, they could offer a direct window into the star's pre-explosion life, revealing everything from its birth environment to the galactic chemistry of its era. It's like finding a diary pages in the rubble of a bomb blast, one that chronicles not just the explosion, but the decades leading up to it. Some researchers even speculate these isotopic oddities might hint at previously unknown nuclear processes, ones where magnetic fields or quantum effects altered decay rates in the star's outer reaches. Yet the most radical theory suggests these anomalies aren't stellar leftovers at all, they're interstellar hitchhikers. The Crab Nebula is plowing through space at breakneck speeds, sweeping up ambient gas and dust as it goes. Some of this material, enriched by older generations of stars, could have mixed with the supernova debris, creating the illusion of primordial matter. The problem: these contaminants should be evenly distributed, not clustered in discrete knots. The nebula's patchy isotope distribution suggests something far more deliberate, like a chef's unfinished recipe with ingredients still separated in the bowl. Whether fossil or fluke, these isotopic quirks force us to rethink how supernova recycle matter. For centuries, we've assumed these explosions blend a star's contents into a uniform soup. The Crab Nebula, true to form, laughs at that assumption. It serves up a chaotic buffet, instead one where the oldest flavors might still linger on the cosmic tongue, defying both time and expectation. And as telescopes grow sharper, we may yet find more of these ancient crumbs, each one a clue to the universe's untold stories. Peering into the Crab Nebula's chaos demands more than just telescopes. It requires an arsenal of cutting-edge tools, each peeling back a different layer of this cosmic onion. Take the James Webb Space Telescope, for instance. While Hubble captured the nebula's dazzling filaments in visible light, JWST infrared eyes reveal hidden landscapes, cold dust veins weaving through the wreckage, invisible shockwaves etching themselves into molecular gas, and ghostly halos stretching far beyond the nebula's visible boundaries. These observations aren't just pretty pictures, they're forensic evidence. By measuring how infrared light scatters off dust grains, scientists can reconstruct the nebula's 3D structure, uncovering cavities carved by the pulsar's winds and pockets where supernova debris never fully mixed. Yet even JWST struggles with the Crab's hyperactivity. Observing this nebula is like trying to photograph a fireworks display with a slow shutter camera. It changes faster than many instruments can track. That's where neutrino observatories like IceCube step in. Buried deep in Antarctic ice, these detectors catch ghostly particles flung across space by the nebula's most violent events. When a neutrino from the Crab zips through the ice, it occasionally smashes into an atom, creating a faint blue flash sensors can trace back to its origin. These cosmic messengers bypass the nebula's visual chaos entirely, offering direct windows into particle acceleration processes near the pulsar. The challenges multiply when studying high-energy phenomena. Gamma-ray telescopes like Fermi catch photons packing billions of times more energy than optical light, but pinpointing their exact origins within the nebula's tangled web is like identifying which drop in a waterfall sparkled brightest. Meanwhile, X-ray observatories like Chandra face the opposite problem. Their razor-sharp resolution reveals structures as small as our solar system. But the Crab's X-ray output fluctuates so wildly that exposures require meticulous timing to catch specific events like flares or jet oscillations. Radio astronomy adds another layer of complexity. Arrays like the Very Large Baseline Interferometry Network combine dishes across continents to achieve resolution so fine they could spot a baseball on the moon. These reveal the pulsar's magnetosphere in real time, tracking plasma waves and magnetic kinks. But the Crab's radio emissions are so intense they often overwhelm sensitive equipment, forcing astronomers to develop specialized filters just to avoid frying their receivers. Perhaps the most revolutionary tools are computational. Supercomputer simulations now recreate the nebula's magnetic turbulence down to quantum scales, helping decode why particles accelerate so efficiently here. These digital labs let scientists tweak variables impossible to isolate in nature, testing how the nebula might behave with different pulsar spin rates or magnetic field configurations. Yet even these models struggle to keep up. The Crab's sheer unpredictability means simulations frequently lag behind new discoveries. What ties all these approaches together is their shared revelation. The Crab Nebula refuses to be studied in isolation. Every wavelength, every particle type, every simulation reveals contradictions that force us to rethink not just this object, but the fundamental physics governing our universe. From JWST icy infrared vistas to neutrino detectors' subterranean flashes, each tool paints part of a picture still maddeningly incomplete, a reminder that some cosmic puzzles demand every trick in our arsenal just to glimpse the edges. Even after centuries of study, the Crab Nebula still guards its deepest secrets like a cosmic vault. Despite every breakthrough, fundamental questions linger, enigmas that could rewrite entire chapters of astrophysics. Take the dark matter puzzle. The nebula's filaments accelerate in ways that visible matter alone can't explain, hinting at invisible mass warping space around them. Is this dark matter left over from the supernova? Or could it be something more exotic, quantum debris frozen into strange new states during the star's collapse? Current telescopes lack the resolution to tell, leaving scientists to wonder if they're witnessing the ghostly imprint of physics beyond the standard model. The answers might lie in the next generation of space missions. Projects like LISA, the Laser Interferometer Space Antenna, aim to detect gravitational waves at frequencies too low for Earth-based observatories. While LISA primary targets are merging black holes, its precision could also capture whispers from the Crab pulsar. If those hypothetical space-time ripples finally appear, they'd reveal whether the neutron star's eerie gravitational silence stems from perfect symmetry, or something far stranger, like a quark matter core bending the rules of relativity itself. Meanwhile, advanced gamma-ray telescopes like the proposed Amigo X mission promise to dissect the nebula's particle storms with unprecedented detail, tracking elusive positrons back to their birthplaces and potentially spotting exotic decays that hint at new physics. On the ground, upgrades to neutrino detectors like IceCube could turn these ghostly particles into cosmic tour guides. Future arrays might pinpoint neutrino bursts to specific regions within the nebula, exposing hidden particle accelerators buried in the chaos. And with JWST now peering into the nebula's infrared shadows, astronomers are closer than ever to identifying those enigmatic ultraviolet absorbing molecules, or confirming whether the nebula's dark spots harbor matter unlike anything we've seen. What makes this era so thrilling isn't just the technology, it's the sheer unpredictability of what we might find. The Crab Nebula has spent a millennium defying expectations, and there's no reason to think it's done. Every unanswered question, from the gamma-ray hiccups to the isotopic anomalies, is a loose thread in the universe's tapestry. Pull one, and the whole fabric of astrophysics might unravel, only to reweave itself into something even more extraordinary. One thing's certain, the Crab's next act promises revelations that could make its past mysteries look like mere prologue. From its pulsing neutron star heart to its ghostly light echoes, the Crab Nebula doesn't just defy expectations, it rewrites them. This cosmic wreckage is a laboratory of the extreme, where particles outrace light in optical illusions, gamma rays flare without warning, and magnetic fields twist into knots that laugh at our models. Every filament, every flicker, every unexplained hiccup in its emissions forces us to reconsider what we thought we knew about stellar deaths and about the universe itself. Think about it, we're witnessing a supernova remnant that shouldn't be this energetic 1,000 years after the explosion. Its pulsar's glitches mock our understanding of neutron star physics, while its gamma-ray tantrums suggest acceleration mechanisms we've never imagined. The nebula's polarized light paints a masterpiece of magnetic chaos, and its vanishing radio voids hint at shadowy processes we can't even detect directly. Even its dust grains seem alive, jerking through space as if tugged by invisible marionette strings. And then there are the questions we still can't answer. Why does it produce positrons like a cosmic factory? Where are all the heavy elements the supernova should have forged? What's silencing its gravitational waves? Each mystery peels back another layer, revealing just how much we still don't understand about the forces shaping our universe. But that's what makes the Crab Nebula so extraordinary. It's not just a relic, it's a teacher. Every anomaly, every contradiction is a clue waiting to be deciphered. And as new telescopes and detectors come online, we're bound to uncover even weirder phenomena hiding in its depths. So tell us what captivates you about this celestial enigma. Is it the pulsar's precision, the filament's eerie beauty, or the way it keeps rewriting the rules? Drop your thoughts below and let's keep unraveling this cosmic puzzle together.